set up. Yay! Shut up, man. Okay. It's AI hacking time. Announcements. First of all, y'all should order club shirts and hoodies. They will have a better version of this design. This is our current work in progress, but SIGPwny merch is cool, and we haven't made any in like a hot second, except for the fall CTF shirts. So y'all should get some. Also, the Japan House Social is this Sunday. Everyone should come. I don't care if you're busy. You should come. It'll be like actually warm-ish for once. What's up?
Are we meeting at Japan House, or are we like meeting at
So I don't think we've planned that yet. We could do like it's a little far to like do a walkover or anything. So probably prefer to meet at Japan House, but we can coordinate like pickups and stuff if some people are driving over and some people don't want to take the bus. We'll figure it out closer to Sunday. But y'all should come. It'll be really fun. And Japan House is really pretty. And I might bring food. So that's cool. This is why people are coming for my food. I respect it. All right. The meeting. I don't think the meeting challenge is.
I'm adding the flag right now.
Yeah, CTFD tweaked on me when I tried to add it, so it will be here. But lovely relevant XKCD about Rocco's Basilisk, which is not true. But whatever. The AI can come for me if it fucking exists. Cool. But today's meeting is about AI hacking. This is the in-depth version. So I have like two versions of this presentation that I've given previously. One is like an intro to like what AI security means, because the definition doesn't really exist and can mean like several different things. This is about how to hack AI. So this is what CTF challenges are about. So y'all can replace me, which is pretty cool. And also just about like what the security of AI looks like. So this is breaking models, stealing models, everything actually AI related instead of just like AI for malware. So background, what is AI? How does it work? Why are you not working? There we go. What is AI? It's math. People think of AI as like some kind of like black box. It's doing magic. It's not. It's all really fast statistics, right? So if we look very closely, this is what AI models look like at a very simplified level. So the image on the left, this one, is what like neurons look like, right? So you have like this entire explanation is very simplified. It covers several classes, from like 440 to like 562 and onwards. So if people are watching this back or like know what they're talking about, don't at me. I know what I'm doing, but this is a very simplified version. But like these are neurons, right? And they are connected, and together they are trained to produce basically a massive graph. It's like 5 million dimensions. It's not possible to like think about it in like normal terms. But at the end of the day, it's a graph, right? And the goal of most AI is to optimize for the local minimum or the global minimum. Usually you end up finding local minimums, but over some problem, right? So you have this like massive graph that is like the mathematical version of whatever problem you're trying to solve. So computer vision, LLMs, everything, it's all graphs. And you're trying to find some minimum that means that you've solved your problem effectively. How do we make these AI models, right? So how on earth do you get like an accurate graph? Because you can generate any like 40 billion dimensional graph any day. But like, why is it accurate? How does it work, right? And so you are performing what is known as gradient descent. So the optimization on like whatever problem to minimize an error. And this depends on many features. Like there are different ways to do gradient descent, like there are different optimization functions, whatever. But at the end of the day, you are trying to go towards a global minimum on a graph, right? And there is something known as a learning rate, which is just like how much you step down the graph every time you like try to take a step, right? So big learning rates mean that you are stepping like really big, but that can be a problem if you are close to the global minimum, right? Or to a local minimum, because you're stepping like right over, and you never actually reach the minimum that you may reach with a smaller learning rate, right? So there are all sorts of tricks to optimize learning rates. Like sometimes you can use like a scheduler to like you know, have a big learning rate at the beginning, so that way you like get to a minimum really fast, and then you can optimize over that like smaller search space instead of having this like tiny learning rate and just like stepping over the entire thing and taking like a million years and like 5 different like massive GPUs, right? Like no one wants to do that. So like there are all sorts of different ways, but at the end of the day, you're performing gradient descent. You're iterating over like your training data multiple times, right? So if you are training like computer vision or like anything image related, right? Like you'll have like a million images. For LLMs, it's like the entire internet's worth of text, right? You have a ton of training data. And that is what your like model is learning, right? And each iteration is like an epic. It like you're going over a whole bunch, you're like learning things based on the data you're given. And there are like things known as loss functions to determine the performance of a model, right? So this is part of what creates the graph. Is like how you define like how well the model is doing, right? So it can look like many different things depending on like what exactly you're trying to train. But higher loss generally it means that the model is doing worse. So you want your loss to be as small as possible. That is why it is a minimization problem. You are minimizing over the loss. How do we break this, right? There are so many mathematical assumptions being made, and like there's so much math being performed here, right? And so AI can be insecure in a bunch of different ways. You can have data set issues. So if your data is incorrect, if it's processed wrong, your model will be incorrect in ways that are often maybe a little hard to debug, right? If you have one image that's somehow been classified wrong, and now your model thinks like a cat is a horse, like how do you recognize that? You don't. You just wait for it to perform badly. But that is why like data sets are super, super important, and correct data sets are super important, because if your model can only learn what's in your data set, right? Like garbage in, garbage out. So if you give it garbage or you give it something that is malicious, hint, hint, then it will maybe learn incorrect representations. You can also have model issues. Like maybe there are ways to trick models, right? And they may also like there are certain models that companies don't want you to have, right? Like they would rather it be proprietary. There are ways to extract those, or to at least like functionally have a representation of like this model that a company doesn't want you to have because it's making money off of it, right? So we'll look into all of those in like 2 seconds. First attack, poisoning. This deals with your data set. So basically what an attacker is trying to do here is, given a data set that an AI model is going to be trained on, can you put in malicious data designed to make something, like make the model learn as bad as possible? And so it will learn incorrect information, right? So like in your cat is a horse example, if you have mislabeled data, you have labeled horses as cats, right? In that case, your model is going to think it's a cat. And if your data set hasn't been cleaned, then it may learn incorrect assumptions. This is only possible if the attacker has access to the data set somehow before model creation. So before the model has been trained, right? Because after the model has been trained, if you like fuck with the data set, your model already exists. So this attack doesn't really work. This is also important to consider in situations where your model is being trained using human feedback. So for the AI people in the room, RLHF, reinforcement learning with human feedback. If you are training something via human responses, what if you have someone who just like got hired and wants to mess with you as much as possible? What if you have someone who's just like absolutely like phoning it in, right? Those are situations where your data set may not be correct. That's bad for the model you will train. How is this used, right? Data set poisoning, sure, might be fine. Has anyone in the room heard of Glaze? Couple people. Cool. What Glaze is? So it was designed, it's a research project from the University of Chicago by a very, very cool team. Basically what it does is artists want to protect their artwork from like being used as part of like Stable Diffusion or like Midjourney, like all those like art generation things. Like artists don't want their art in those systems, right? And they don't want those systems to learn how to represent their art style correctly. So like given like there are so many like AI things where you can be like in the style of XYZ artist. And if that art is in its data set, it might like the AI will try to spit out like something that looks reasonably similar to the work of this artist, which people don't like. And so what this does is it essentially adds, very simplified again, it attacks the original, or it cloaks the original artwork using adversarial attacks. So to the human eye, it looks fine, right? Like the top left and top right look identical to people who are viewing it. So the artist still retains their viewership. They can still like post it on Twitter and it'll be fine. But consider someone scrapes that artwork off Twitter with the intent to use it in whatever model, right? In that case, the artwork is cloaked in such a way it has been poisoned. So when someone trains a model on this image and tries to generate something in the style of XYZ artist, if their images are cloaked, then it should fail to mimic the artist. So it'll produce like garbage instead of, pretty painting or whatever, right? This is a dataset poisoning attack because what you've done is you've posted what is essentially malicious data that like, people who are viewing it, it's fine, it's whatever. But to a model, this is labeled incorrectly, it doesn't look right, whatever. But this is imperceptible noise, right? Like you can't tell unless you've seen it or like know that it's cloaked. Yeah, what's up?
Sorry, is Glade, is that different from Nightshade?
It's by the same people. So I don't know the specifics of Nightshade. I haven't had the chance to look at it, but it is, I believe, a successor to Glaze. They're intended to work together, but it's from the same research lab and by the same people. What's up?
So is Blaze like, I guess, specific to one like image generation model, like Stable Diffusion or something, or is it like work across?
In theory, it's not supposed to be. In reality, I don't know how much testing has been done on what exactly the effectiveness of like cloaking attacks like these are. This is like Glaze is like a year old, I think. So not like it's not like super recent, but it's not super old either. So it doesn't have like a ton of like research surrounding like the specific effectiveness of that. But soon I think people will start to have those questions because like this is something important to artists. What's up?
So how exactly does it change the original image without changing?
I will get into that.
Um,
Give me a hot second. I will get into that. Any other questions before I move on? Cool. So that's poisoning attacks are data set specific, right? What if the model's already been made? Right? Like, let's say like there's a facial detection algorithm or something where like you don't necessarily have data set access. That's what model evasion is. So taking a slight step back to your question, how do we produce adversarial examples? Right? It's input designed to fool a model into undesired behavior, right? Whether it's misclassifying artwork, misclassifying faces, but it should be imperceptible. So let's look at an example of an adversarial attack before I kind of get into how they're made. So you have a pig. Let's add some very tiny noise. Like this is scaled up, right? Like this is like a tiny square and you add that over and over and over again. Now a model thinks it's a plane. Hence my meeting flag, when pigs fly. With AI adversarial examples, you too can make pigs fly. That's crazy. This is a joke I did not make. This is by, this is pulled from Alexander Madry, I think is his name. He is at OpenAI and also MIT faculty. Not an original joke, but I think it's funny. How do we create adversarial examples, right? The answer is complicated. I am going to give you a very oversimplified explanation. It is an ongoing area of research, right? Because this is like fundamental to most like attacks, right? Is how do we create these? The most intuitive methods use gradient ascent. So you know how like AI models are intended to use gradient descent, right? What happens if you try to push an image to be the worst possible, right? That's gradient ascent. Of course, this assumes that you have access to some sort of gradients to ascend, because the gradients are only really produced by the model, right? There are many ways to do this, some of which don't require having access to the model, some of which do. Again, ongoing area of research. But essentially you're just trying to push an image to be the worst possible. You don't want to take it too far, because then obviously the noise starts to show. And some attacks are better than others. But this is kind of what they're doing at the end of the day. Again, like I said earlier, you don't need to have access to the model or its gradients. It's nice. Like white box attacks are obviously really nice because like in an ideal world, you do have the model, but there are various attacks that still work on black box models. One property that helps, there have been papers showing that attacks are transferable. So attacks that work on one model can often transfer to an unknown model. This is why I said that glaze may or may not work on other models. It really depends. I have not read into the research about whether this works. I don't know if it exists. It might not. But I do know that this exists for other classes of models where you can use surrogate models trained on similar data. So like kind of an approximation of the original model, right? Like you can't just like do it based on nothing. But you can create adversarial examples against an unknown model. These methods usually require like something known as oracle access, stolen from friends, where you have access to the output of the model you want to attack, right? So like, say you have query access, so like your ChatGPT, right? Like you don't have access to ChatGPT, you don't have access to the GPT model, but you can talk to it, right? So you don't have the weights, but you have, you know, its output, and you can kind of use that to create a surrogate model that works mostly the same as the model you're trying to attack, and then kind of go from there and attack the model that you have. Very fun. I'm summarizing a bunch of papers here. How do we defend against this, right? Like, if these attacks exist, how do we stop them from happening? Because that's also an ongoing area of research. The most common defense I've seen is adversarial training, that incorporates adversarial examples into the training process. So like you mess with your input like a little bit during the training process, and then like that adversarial example may no longer work because you've already trained your model to be like robust to that, right? Where it's like, yeah, this is a cat, and then you fuck with it a little, and then you're like, this is also a cat. Model learn, and it'll kind of start learning, like maybe like it won't be as susceptible to noise, essentially. There are also defenses that help prevent the attacker from gaining access to gradient information. So like, say you don't like you don't want like your attacker to like have access to a model. Like there are many ways to like defend against that. One example is defensive dissolution, which y'all should look into. It's very interesting. Extraction attacks. Say your company has a model or a company that you don't like has a model, and you want that model, but the company makes money off of that, right? Like they're not going to give you model access. How do you extract the model? Given Oracle access or query access to a private model, there are ways to extract the model. And it may not be as accurate, but it can approach the accuracy of the original model. So like if you have like a cat or dog model that's private, if you like send it enough images, you now have a training data set, right? Because you have the images that you sent and what the model gives back. And from there, you can train your own model because now you have a training data set, right? This, like I explained earlier, it can be used in combination with other attacks. Because like, if you've extracted a model, it's no longer a black box attack, it's a white box attack. And from there, you can do like evasion and all sorts of other fun stuff, right? whatever it's here for. CTF examples, woohoo! There aren't many CTF challenges. We're starting to have more with adversarial examples. I've written a couple. I intend to write one or two, hopefully, for UACTF this year. Do not hold me to this if this doesn't happen by summer. But let's take a look at a challenge I wrote several years ago at this point. Good lord. What are some tools that you might want to use? PyTorch, Torch Vision are PyTorch tools for like images, and I maintain PyTorch supremacy. It is better than TensorFlow, and I will die on this hill. Everyone who knows ML agrees with me because I'm correct. There's also a package called Torch Attacks, which I uses PyTorch, but it implements a lot of attacks for you. So y'all don't need to know the specifics of like PGD or whatever, right? Like you can just like import PGD, use on image, submit. Good night. I stole Torch Attacks from a CTF, from like a write-up of this challenge that I'm about to show you. But it's useful. I highly recommend. So what is the challenge? This is Ponies Please. It's from UACTF 2021, I think. Time is fake. But the intent of this challenge is you are given images of horses or ponies. You need to make an AI model that's working on the back end think it isn't a horse. But it should look similar enough to the original picture. So you can't submit garbage. You can't submit images of not horses. You have to submit this image with modifications. And you have to do it 50 times. So you can't really do it by hand. I think people tried. I don't know if any of them succeeded, but you shouldn't be doing this by hand because why are you editing 50 images of horses by hand? Don't do that, right? So essential goal, fool a model into thinking horses are not horses. Prime example for adversarial attacks. I'm going through code. Not all of this needs to make sense to you, I promise. But the main thing here is you can import PGD. PGD, I rolled my own because I had the code already because this is my area of research. You can also just import it from various Python packages, but PGD is your adversarial attack, right? So given the image you want to pass through it, you can just generate the adversarial example and then pass it through your whatever. So this is how these are created, right? Like I believe this is how I this is how I trained the image or the model. What's up?
What does PGD stand for?
Projected gradient descent. I know I said earlier like gradient ascent is used for a lot of this. This is basically just gradient descent into something that isn't the original label. So given horse, make them all cats instead. It meets the purpose, right? What's up?
Do you need an NVIDIA GPU or like a CUDA capable GPU to train these models?
So a lot of the times, yes, unfortunately, just because like running models takes some GPU compute. You probably could do it on a CPU. It might just take forever. So yeah, but a lot of AI stuff does require GPU. You can get free ones though.
Does AWS offer compute instances where you can train these models?
AWS does. Colab offers free GPUs. So people who like want to use free compute usually have like Colab instances open. Highly recommend Google Colab. Hopefully they don't get shut down anytime soon. But like yeah, there are ways to access free compute. But I feel like okay, it's been like 2 years at this point, maybe 3. I feel like I generated at least one adversarial example using my laptop. It just takes forever. So wouldn't recommend, but you can do it. But
The once you have your adversarial example, you can just submit it back to in this case my challenge, but whatever challenge. A lot of CTF challenges, even now, still kind of look like this. In some cases, they'll have more restrictions where it's like, oh, it has to, I don't know, like it. There was one challenge recently that I worked on, and I forget the exact restrictions, but it was like, it needs to look similar to the original thing, and just a couple other restrictions. But you can add all of those when you generate the adversarial examples. Like you can just add that as part of like your training. What's up?
How do you like check similarities? Is it just like some kind of where?
So, yes, I believe it was just mean squared error, when I did it, with some tolerances. And I do remember what the constraints were. It was like, it had to, once you submitted the adversarial example, it went through like a random crop and like, one other random thing. But like, it just something to like fuck with the image afterward, right? Where it was like, oh, and JPEG compression. That was the other one. So like it sounds hard, but what you had to do was just add JPEG compression and random cropping into whatever you were using to generate your adversarial examples. And yeah, like that was just the easiest way to do it. So like a lot of challenges for AI challenges that look like this will just be like generate adversarial examples given some constraint. And that constraint can look like various things, but you will just train against that constraint. And yeah, hopefully that makes sense. If not, feel free to like yell at me. And I'm happy to show you like more examples on my laptop. Or just come up to me at like a CTF or something. Anyone have questions?
Yeah, is there a way to like, I guess, outside of doing it by hand, do attacks on like the parsing or tokenization to get AIs to generate things they shouldn't? Like I know there's the infamous like my grandmother tells me bedtime stories about napalm one.
Right.
Which I speak to. Can you do that like programmatically? Do you just have to kind of figure it out by
So yes, attacks on LLMs do exist. They look a little different to the ones that I've presented, because it's text. I'm not as familiar with them, because my research has been very image heavy. But as far as I'm aware, like you can do things like flip word meanings or like flip like letters, and like now you're like inputting gibberish, but you can get it to do things that it should necessarily do.
Okay. And you can do that like programmatically?
The same stuff applies where it's like, you're like, maybe performing gradient ascent, descent, whatever. Or just grid searching over a space, by like flipping letters around and seeing if that produces something weird. There are a lot of ways to do it. Again, not as familiar with LLMs, so I can't give you like a ton of detail. But you should go looking for papers because they exist. But yeah, what's up?
Yeah, it's something like JPEG compression. It's not really like differentiable, is it? Or
So you can add it to the pre-processing for an image before it goes in to be adversarially attacked.
okay. Oh, okay. So before, all right.
At least I believe that's how it was done. Any other questions? Awesome. Well, in that case, next meetings this Sunday, Japan House. Be there, be square, bring food. I will bring food. Bring blankets. Hopefully, like it should be warm. Maybe we'll see a flower. Who knows? And then next Thursday, no meeting because we're going to CypherCon. Woohoo! For the people coming on that, it'll be a great time. Anyways, thanks, friends. That's my 1 hour ramble.